Hello, my name is Kevin Casagrande. I'm a DEDP student with the University of North Dakota in the undergraduate electrical engineering program. This is my project demonstration for EE490, Engineering Problem Solving with LabVIEW, in July of 2015. So for my project, I created a MD5 or Message Digest 5 library for use in LabVIEW and provided some top user level functionality for that. Message Digest 5 is a cryptographic hash algorithm. It's a little dated and not entirely cryptologically secure anymore, but it's still used in a variety of applications, especially those that were developed for Windows XP. So it's kind of a useful tool to have if you're going to get into cryptographic work. So a cryptographic hash algorithm, like MD5, it takes a string or file input of a indeterminate size, really any size, up to the specifications of the program. And it reduces that down to a hexadecimal signature of a fixed size. And the idea is that this is done through a non-reversible algorithm such that you can't take the end product and from that determine what the original file contents were, at least in theory. Also, you want to try to reduce the number of collisions. That is, you don't want to have the number of input files that create the same hash as an output. So the MD5 specification is a 5-step process. However, steps 1 and 2 are inherently related, as are steps 3 and 4. So I kind of reduced that down to a 3-step process, and I created a sub-VI for each of those 3 steps. So I'm going to kind of walk you through those real quick, then I'll show you how the overall top-level applications work. So this is the first block diagram for the first sub-VI, which completes steps 1 and 2 of the MD5 specification. Step 1 is padding the file. So in order for the algorithm to work properly, the input string has to be evenly divisible into 64 byte segments. So to accomplish this, we pad the original file with a number of items. First, there has to be a single 1 bit, followed by a number of 0 bits, and then finally a 32-bit representation of the file size, and that's the original file size. So for example, if you have a certain file that is not quite 64 bytes in that last segment, then it's going to add that a number of zeros plus the 32 bytes such that the total size now is a full 64-bit block. As a result, there's really 2 possibilities when we get into the remainder size of that file. Either that's less than 55 bits, as shown here in this case structure. So after we divide the original file into 64-byte segments, that remainder piece, that last segment, if there's sufficient room in there for both the 32 bits of file size data and the single 1 bit, for a total of 33 bits remaining in that segment, before we get to a full 64 bytes, then we're going to add those items plus a number of zeros equal to bring it up to that full 64-byte specification. If, however, there isn't room for those 33 bits of information, then we're going to have 2 64-byte blocks. So it'll be the 1 bit plus the number of zeros to bring it up to a full 2 bytes of 2 64-byte blocks, and then the 32-bit file size. So as you see here, what happens is I take the string input, this is going to be whatever our source string is, and compare that to divide it by 64 segments and determine what the remainder is. If the remainder is 55 bytes or less, then there's room for us to get the remaining data in there. So this case structure provides that input, and it determines the number of zeros that I'm going to need to add between the 1 bit and the 32 bits of file size data. And we build that array here. Here we append the 1 bit. I've got the original stuff from that last segment, and then this is what provides us the 32-bit file size information. Now you note that I need to convert this from bytes to bits. The easiest way to do this, and I got this from a C program that used a similar mechanism to convert bytes to bits, is we shift the 3 significant bits of information from the original file size into the 5th byte in an 8-byte block, and then put the least significant bytes and bytes 1 through 4 in that block, and append that to the original file size. This does provide us a limitation. I can only actually use now 35 bits of information to describe file size as opposed to the full 64. As a result, that means my maximum file size is 4.29 gigabytes. but for our applications that's more insufficient. Then we take that final array and it goes through a typecast function to put out the padded string, which is going to be evenly divisible into 64-byte blocks. Now, if the original file size did not have sufficient room for us to put all that in that last segment, then the case structure, excuse me 1 minute, there we go. So now we have a different case structure for when the remainder is of that size, such that we now create two 64-byte blocks instead of the original one, and that determines the number of zeros I need to accomplish that, and the rest of the application is the same. The bulk of the actual processing is in step 2. So I'll show you that here. This is a bit of a complicated thing, so I'm going to walk through it here. So essentially, each 64 bytes of data is processed by the algorithm independently. So this first loop really does that, divides it into 64 byte segments, and then processes each one individually. Now remember, because we put the padded string in there, this should be evenly divisible to 64 bytes. So for each of that 64 byte segment, we take that data going in, and we take that message M, which is that 64 bytes of data in that segment. We'll use this later as part of the algorithm. We also have 4 words, A, B, C, and D, and they are initialized to these values. That really is step 3 of the specification for MD5. So really that's all just accomplished right here. The bulk of the processing for MD5 is it goes through a series of 4 rounds, and each round has 16 operations where data comes in for these 4 words. It goes through a logic system, which I have here in a case structure, then is outputted to those 4 words, but it's not outputted A to A. So A goes to B, and so forth. This is what creates the rotation required by the algorithm. The other inputs are a K value. These K values are based on sine function and radians of each iteration of step. But that was just easier to save memory and resources and put that in a table. So I have all of those values here. There's also a shift function, and the amount of shift is a rotating degree for each round. So it goes 7, 12, 17, 22, and you can see it goes 7, 12, 17, 22, 7, 12, 17, 22, and so forth. And then the second round it's 5, 9, 14, 20, 5, 9, 14, 20, and so on. So that determines the amount of shifting that is occurring in each iteration. So for the first round, we use what's called function F, which is this logic function here. So I have a case structure for each of the different functions. So the first round is processing the first 16 segments of the message. So, well, really segment's not the best word since I called each 64-byte block a segment, but each sub-segment of the segment. So the first 16 are accomplished with function F. The second 16 are accomplished with function G. The third 16 are accomplished with function H. The final 16 are accomplished with function I. So all that really is changing is the logic function that is being used here. So what's going to happen is that we're going to create a summation. We're going to take the result of this logic function. It's going to be summed with a rotating segment of the or subsegment of the message, the K value, and then that's going to be shifted by a S value and then outputted. And then what happens is that the result of that, after we get through those 64 rounds for the 4 rounds of total of 64 processes, that's going to be added to our original word values and outputted as our new words. And that's the bulk of the processing used for this, for the core of the algorithm. Step 5 is much more straightforward. So in step 5, all we're doing is assembling those 4 words into a single hexadecimal hash. And we do this with A and then B and then C and then D, but we do it in a way such that the least significant byte of A is first and going all the way up to the most significant byte of D. So in order to accomplish that, we first swap the words, basically the high and the low significant bits or bytes for each of these variables, and then we swap the bytes within those words that makes sure that we now have ordered this with least significant to most significant. And then from that we convert that number to a hexadecimal string and append it to a final string value. So again, this will start with the least significant byte of A and go all the way to the most significant byte of D and output our hash. Now you'll note for each of these sub VIs, I put in some error handling. So I've got an error input and error output. And in the event of an error, it just shorts the system. There's no processing, and it just passes the error on down to the next block. And you can see that that's the case for all of these. No error. Right there, it just shorts out the error. And where was my step 1? Same thing here, error, just shorts it, no error. Okay, so with those those 3 sub VIs to create the 5 steps of the message specification, that actually will process whatever is handed to it as the input string and provide whatever it wants to use as the output hash. So towards that end, I've created a couple top-level applications, one for processing files, one for processing strings. So the file hash algorithm, you can see it takes a file path as a user input, it opens it read-only, and then it reads the entire contents of that file in a binary format, passes that on to the sub VI, the first sub VI, which is step 1, which does that padding function. Then it goes to the second sub VI, which does the actual processing loops that we talked about. And then finally it goes to the third sub VI, which does the actual assembly to create an output hash file. And it closes the file that we opened to do that. Incidentally, I have an optional feature here such that you can input a path to a text file which contains a hash you want to compare against the hash you calculate. So similar things that open that file, it'll read the contents, close the file, and it'll put that into the checksum block on the front panel, and it'll compare these two. I do have a capitalization function here just to make sure that we don't have any issues with uppercase, lowercase, because the hash is not itself case sensitive. And if we get a match, then it'll illuminate the LED, the green LED on the front panel to show that the reference file hash and the calculated hash is correct. This is one way of verifying the integrity of the data. So if you calculate the hash at some given point or for a given file, and you calculate it later on, if the two hashes match, then you know that that file has not really been altered. If, on the other hand, that file has been altered, the hashes will be completely different. They won't match at all, and that's kind of one of the primary uses of cryptographic hash function. And you can see here again, I have similar error handling routines should you want to incorporate this as part of a larger operation. So here's the front panel display. Again, user inputs the path to the file they want to take the hash of. The hash is displayed here. You can put the path to a file for a text file that you want to have a hash for comparison, and it puts that comparison value here, and then the LED illuminates if the two hashes match. Also have a function just for strings. So if it takes a user inputted string, calculates the hash. Also, user can put in a checksum value here, and that'll create a comparison, and again the LED will illuminate. This is a much simpler process, kind of very straightforward, but you can see here again, input string comes in, we pass that directly to that padding function to pad it up. Then it goes through the loops to do the processing of the hash, and then finally to the digest function, which actually assembles those and puts out the hash. User inputs a checksum hash. Again, I have a capitalization function to make sure we're not case sensitive, and output to the LED. And again, if there's any errors here, it bypasses all that processing.